What's up, everybody? Today we are going to look at 3 different problems about sliding mode control, and what we are going to achieve is to prove FTS, and which is an acronym for finite time stability. Okay, and for example, we are familiar with the expression GAS, right? Global asymptotic stability, and we will look at finite time stability today, which is of course a strict condition. All right, and there will be 3 problems, and this is problem 1, and it is also known as Wissing algorithm. Of course, it's probable that you will see some variations of that system, and here are the conditions on the parameters. Okay, there are some parameters k1 and k2 in the system given. All right, and the problem statement is the following: finite time stability proof. Okay, and to show the global FTS, finite time stability, following are required. This is a theorem, actually. It's an important theorem, and I will talk more about this in a moment. But first, prove global asymptotic stability. Okay, and then show that the vector field is homogeneous, and weighted homogeneity is something that we will talk about with a negative degree. Okay, and if the system that you have satisfies these 2 conditions, if you're able to prove global asymptotic stability, and also if you are able to show that the vector field that you have is homogeneous, and weighted homogeneity is something that you have and with a negative degree, then that implies immediately that the system that you have has the FTS characteristic, meaning finite time stability, something you have. All right, and this is an important theorem, by the way. Okay, so I will repeat it one more time. And if your system is globally asymptotically stable, and if the vector field that you have is homogeneous with a negative degree, okay, and of course you can also consider weighted homogeneous, okay, and if your vector field is weighted homogeneous with a negative degree, then the system that you have is FTS, finite time stable. Okay, this is a really important thing in sliding mode control field especially. Okay, and so let's prove global asymptotic stability. Okay, and here is the Lyapunov function that we are looking at, and maybe I should zoom a little. Okay, I am looking at my screen. Okay, everything is in order now. This is the Lyapunov function, and it can be seen that this function is positive definite, but it's not continuously differentiable, right? So here it is not like that. This is the set of functions that are continuously differentiable. And okay, so therefore it should be also stated that the system trajectories will not stay in the region where the Lyapunov function is not differentiable. This is another critical information. I am kind of glossing over these important facts, but you shouldn't consider them as details, unimportant details, but the type of proofs that I am trying to show here, you should take it as a sketch of proof. Okay, this is not 100% mathematically and accurate in a way. Yeah, because I'm not trying to show every little detail and every little what type of function is this, for example, what type of set, what type of domain that we are interested in. I'm glossing over those facts. I'm aware of that. Okay, and I want you to be aware of that as well. Okay, and this function, Lyapunov function candidate, is not differentiable for this set. Okay, why? Because this is absolute value function is not differentiable at the origin, right? Okay, so what I'm trying to say is that, and here this is x1, this is x2. When x1 equals 0, meaning this section, we should be able to show that, and we are going to make an analysis, right? And we are going to use this Lyapunov function, and the analysis that we do will not hold in this set, right? And we should be able to show that due to the system characteristic, due to the dynamics that we have, and whenever your trajectories, enter in this, this is a line, of course, but enter, let's imagine as a region enters, you should be able to show that it exists, that region. Okay, and that is something that you should be aware of. All right, let's continue. I will try to keep that really short, and this is again some type of like formula that we use for differentiation and like take an integral of a function. All right, let us differentiate the Lyapunov function candidate, and yeah, using this information we have that, and there will be some cancellations, and here it is. And also look at this. This is something that we know by looking at this directly. This is something that we have now, and here notice that this is not strict inequality, but this is, for example, this is the type of thing that we use like Lassard's invariance theorem, right? And it is almost like whenever you see like v dot this, like immediately the part of your brain that stores, I guess, Lassard's invariance set theorem and should be should get excited is what I'm saying. All right, using Lassard's invariance set theorem, and let's remember in real simplistic terms, okay, this is our dynamics, and f is continuous differentiable function, and I written that here in short, and v is also continuous differentiable function, and because we would like to differentiate it, and also we would like to be able to show that v dot is also continuous, right? This is why these are the type of constraints that we impose, I guess. And all right, the trajectories converges, right? Trajectory, equal trajectory, and each trajectory, I should say, converges to this set, okay? And this you might understand. However, this is something maybe you shouldn't like see it immediately, right? And that is, one would also say, this is the only reason why mathematicians exist, and we should take and use their theorems for this Lyapunov function. Okay, so here is the dynamics, and each state trajectory converges to this set. Okay, and if you can show that this set is origin, then you would be able to show that, okay, the system that you have is asymptotically stable. That's a great thing to be able to show. Okay, but in this form, this cannot be used to show the stability, since the Lyapunov function candidate that we have is not continuously differentiable. Okay, and however, like strictly mathematically, we cannot use it. We cannot take advantage of this theorem. However, there is an extension to that theorem, which is Lassalle's invariant set theorem, and which only requires the Lyapunov function candidate to be local ellipsis continuous, okay, and local in the region of interest. And it can be seen that x1 also goes to 0, and like from this we know that x2 go to 0. Okay, and also using this like extension of the Lassalle's invariant set theorem, we are able to show that x1 goes to 0. So x1, x2 goes to 0, and hence the global asymptotic stability, and hence the asymptotic stability. But also, since we also know that v and v dot is radially unbounded, okay, and what I'm trying to say is that v is positive, right, in the whole R2, and v dot is negative in the whole R2, right? And okay, then we are able to say, like, we are able to make a claim about the global behavior of the system. Okay, and hence the global asymptotic stability. Okay, and let's look at the weighted homogeneity, that expression. And by the way, I took that screenshot from, let me write the name, Shyam Kamal. This is a YouTube channel. He is a professor in India, and he has a YouTube channel, and the name of the YouTube channel is this. Okay, this is AMAL. Okay, and you can check, and he has a great, and I mean it, great sliding mode control course. There are almost, I don't know, 25 lectures over there about sliding mode control. Of course, there are like other videos on that about control as well, and I highly recommend it. Okay, and okay, he was the inspiration for this video, I would say. And okay, this is the validation. I will skip over this, and or I will go over it. And here is the dilation. Like, this operation is defined as given, and here is the vector field. This is the vector field of interest, and the vector field with the dilation is that, right? And here this is 2 and this is 2. Okay, and here this is 1 and this is 1. Okay, you might be saying, what are you talking about? I will explain it. And here is the m. Okay, this is the m. All right, m is -1. Okay, now I will explain it, what I was trying to talk. Okay, wait a sec, let me change the color. All right, now it's great. And weighted homogeneity. Okay, I will show it for n equals 2. And okay, this is the, let's imagine a function. Okay, lambda to the power of p1. Okay, and here lambda to the power of p2. All right, and if you are able to write this expression in this form, that means your function is weighted homogeneous, and m is the homogeneity degree. Okay, and this is the dilation operator that we use. Okay, of course, I show it for n equals 2, but of course you can show it for other dimensions as well, right? And yeah, there is a theorem which I stated at the beginning of this page, I guess. Yeah, we already proved the global symmetric stability, but we need to show that the vector field that we have is homogeneous and weighted homogeneous with negative degree. Okay, this is important, and this is a really important property of a system. Okay, and here we are able to show that, like this, and the homogeneity degree of that vector field. Okay, and here is the vector field is f equals f1, no, x1 x2, right? All right, this is the vector field that we have, and the homogeneity degree is m equals -1. And since this is a negative number, and gas and weighted homogeneity with m less than, with negative m, implies FTS, finite time stability. Okay, of course this is something that I haven't talked about this, mentioned about in my previous videos, and this is something I will talk more about. The weighted homogeneity property is something that we care about, especially when we are talking about like sliding mode controller type of problems. Okay, here's the problem 2. I will be quick about this. Prove FTS, and let us use the following Lyapunov function candidate. Again, this is candidate because, like, the expression that innocent until proven guilty, that type of thing is the case here. And this is the Lyapunov function candidate, and probably when we write, we can write it in this form, right? And we will try to find an obvious positive function, and then what we need to do is to show that v dot equals 0. And when we are done with proving this expression holds and this inequality holds, then we can say that okay, that was actually a Lyapunov function. Okay, valid Lyapunov function for this, to prove the stability of the given dynamical system. Okay, and let's look at the v dot expression. I will not go over every detail, and you can guess, right? Here, d over dt is sine x times x dot. Okay, and x is x of t, right? Okay, yeah, I didn't show that. Yeah, and this is the expression that we took advantage of. Right, here's the thing, right? V dot, and then we are basically doing some simple algebraic manipulations, and then this is what we have. And let's recall the requirement for finite time stability when we are trying to prove that by means of a Lyapunov function construction. And this is the requirement where k is positive and alpha is some real number between 0 and 1, and it can be 0 as well, right? This is not strict inequality. And here in this case, since we were able to show that, and we can write k equals 2 and alpha equals 0, and hence FTS. Okay, let's look at the problem 3. And I am looking at my screen. Okay, you can see that. All right, And here, this is also called supertwistting algorithm. This is the dynamical system. We have input, and this is input where we also parameterize and use the phi function, and phi function even like that. Okay, notice that 2/3 and 3/2. Okay, because some author made a mistake about it, and I lost a lot of my time about trying to figure that out. And yeah, that was kind of painful, and that is the reason why I'm kind of doing this video, because I mean, supertwistting algorithm is a well-known fact in control engine, control theory, but for some reason it might be the case of regarding the YouTube's algorithm. And I tried to search for a video, and I couldn't, I don't know why I couldn't find a valid video about it. Okay, that's why, yeah, that's the reason of me doing that video, I guess. All right, let's prove global FTS, and for this system, let's use that Lyapunov function. Here, this is the Lyapunov function, and let me tell you this, and why we would use this is not obvious, and it is not like v being positive on R2 is not even obvious too. Okay, and that is like at this stage you would know that, okay, that is going to be a heart, like there will be bunch of hearts and not so obvious, I should say, and algebraic manipulations, yeah, to come. Right, this is the v, and first of all, of course, since it is not obvious, right, you should prove that v is positive on R2, and especially if you are trying to figure that out, or if you try to prove global FTS. Yeah, that's why I said like R2 and not D in R2. Okay, and V dot also must be negative in all R2. Okay, let me delete that and try to make some space for myself. All right, and calculate V dot, and I will not derive that from scratch. Okay, here is the, let's say that is given to you, and this is the V dot, you derive that, and okay, continuing, and V dot, this is V dot, right? And let us prove that the stated Lyapunov function is positive definite. And first, let us focus on the negativity of the, V dot on a closed curve and circling, right? And all right, yeah, here is the closed curve. Here is the closed curve like definition, and this is the set, right? And to be able to draw that, you have this MATLAB code, okay? And here this is phi, and 2/3, and this is y. All right, I'm suspecting that I kind of made a little mistake about the editing parts of that YouTube video, not the mathematical derivations, hopefully. And so you can see that set, okay? And this is a closed curve and circling the origin, and this red dot is the origin, okay? And let me delete that. And you might be asking, why would we care about positivity or the negativity only on that set, only on that closed curve encircling the origin? And I will come back to that. Okay, so if you look at that expression, there are two ways, like two sub cases that you should analyze, and one of them is that case and other of them is that case. Okay, and yeah, when that happens, v takes this form, okay? Because remember, we are trying to prove that v is positive and v dot is negative, but let's focus on v being positive in R2, okay? We are trying to prove that, okay? And that is the goal. And now we are trying to prove that in this given set, okay? And we will prove that, and then we will use some trait or property of v, and then we will be able to prove v being positive on the whole space, okay? And yeah, if you do the required manipulations, you get this V. All right, and again, after some manipulations, you can see that V is strictly positive. And this is important. I'm not like stating V can also be 0 on this and closed curve encircling the origin. I'm not talking about that. I'm saying V will be positive, strictly positive on this, yeah, closed curve encircling the origin, this set. And okay, again, this is another sub case that we should look at. And again, after some manipulations, we are able to see that V is positive, strictly positive. And since these are the two cases that we need to look at, and because of this, the definition of that set, and we can state that V is positive on this set. Okay. And you might be asking why that is important. We are trying to prove the positivity on the whole space, on the whole R2, okay? And I will come back to that. And here is the reason. V is a homogeneous function. Okay, this is like, you should kind of know that. And if you are trying to learn more about like sliding mode control and that type of control strategy, and homogeneous functions are one of the things that really matters in this field. All right, and if you check this, right, equality, you'll see that that is the case, right? And here that is weighted homogeneity, right? And you can write this, and this means that V is like homogeneous, weighted homogeneous. Okay, and K is positive on the whole R2. Okay, and all right, so therefore the following statement can be made. Of course, there are some things that I'm kind of glossing over, or I'm not doing a great job of like elaborating my argument here, but you will understand. I'm hoping that the following statement can be made, which is the following: for every xy in R2, there exists a k which is positive, such that this pair is on that set. Okay, so meaning okay, let's imagine that was a closed curve, okay, and we are saying that, and V of xy, right, this is x and this is y, and whatever, let's say this is x0 y0, whatever x0 y0 pair you give me, and I can find a k such that and this expression, and here in this case a 3 over 2 a x0 y, wait a sec, k times y0, this pair is on this set. And since we know that this set, on this set V is positive, we are done, right? We are basically completed the proof of V being positive on the whole R2. And here's another information, like really important information, and you know the dilation, right? And let me try to say it again, like dilation that we use, right? Dilation that we use is here a32 and x a y. Okay, this is dilation for k positive, and this is dilation, and this dilation operator is also a map from R2 to R2. Okay, and that is actually important. That actually help us like proving that, okay, V being positive. And now we need to prove V being positive, and then V dot, be negative, and then something like that, right? We should be able to prove that. And at the moment we are done with the first part. Okay, so let's try to prove V dot being negative on the whole R2, and let us prove that. And again, that is that. And by the way, let me tell you, you should change this with positivity of V. I guess that was a mistake. Other than that, there is no mistake, by the way. Okay, that's everything is cool. Okay, and again, this is completely correct. That parts, this part was the part that you would like. This is positivity. Okay, change this negativity line word with positivity. Okay, and let's continue. Again, let me show that in a clear way. Okay, this is the MATLAB code to be able to yeah, plot this and lever set and closed curve encircling the origin. All right, let's look at that. There are again two categories, two special cases, and one is that and one is that, because only these two cases would lead to this conclusion. All right, and let me delete that mess. And here, when we are done with the manipulations, okay, and here we are using this equality and inequalities, we can see that I'm not like showing all the derivations, of course, and v dot is strictly negative on this set. This is important. And again, for this case, we can show that v dot is, wait a sec, v dot is strictly negative. This is important. Therefore, since there are two cases, and in those cases we were able to show that v dot is strictly negative, at the end we can say that v dot is strictly negative on this level set of that expression, and closed curve encircling the origin. Okay, all right, again, what we want to show is to show that v dot being negative on R2. All right, and we just show that v dot being negative on gamma. Okay, gamma is the set that we are looking at right now. And again, let me delete this to make it clear. Here, okay, we are continuing, and v dot is a homogeneous function. Again, the same argument that we are making. And since that is the case, and the dilation operator is mapped from R2 to R2, okay, and therefore the following statement can be made: for every xy pair in R2 that you can give me, there exists, meaning I can find a corresponding, okay, and probably it will depend on x, y that you gave me, all right, and such that this expression is on that set, okay, and by using this expression immediately leads to conclude that v dot is negative, okay, on the whole R2, by the way, okay. And I didn't write R2 because here, look at it, this is not that, okay, and this is either or something like that, you know, in the Word or LaTeX, right? This is, you know, the matrix A, right, like matrix B greater than, right, and or maybe I should write matrix B minus A is positive definite, right? That type of, like that symbol that I'm talking about here, okay, because for the positivity of a function or a polynomial, that is the thing that you can see in the literature, okay. That's why I want to show that. So far, global arithmetic stability has been proved for the given system. For global finite time stability, we need to be able to show that that is the case. And so far we prove global stability, and we want to prove FTS, finite time stability. And let's continue with the operations. Let us remember the homogeneity property of the v dot. All right, is there a problem with the screen? No, okay, everything's fine. And I can write, right? Okay, there's some, anyway, okay, this is the thing that we written already, okay. And all right, continuing, if we look at this expression, and that, you know, again, this is a closed curve, and meaning this is a compact set, and compact set is some type of mathematical term that matters in the expressions we will derive in a moment. And we know that that is the case. Why? Because we concluded that v dot is strictly negative on that set, right, on R2, we concluded that, and except origin, of course, and that's why we can write this expression where c is a positive number, strictly positive number. Since v dot is negative definite, this is easy to see. on this, like we already concluded v dot being R2, and maybe you're saying, hey, we already concluded v dot being negative definite on the whole R2, so why are we interested about the negativity of the v dot on this given compact set, right? And I will come back to that. Again, we will take advantage of the fact that v and v dot were created in such a manner that they are homogeneous and weighted homogeneous. They have that type of trait, which we will come handy in a moment. And v dot, here we can see that v dot, again, we use the same homogeneity, weighted homogeneity expression. And let's write that again. We have written so far nothing new, and that is the case on that compact set, right? Okay, I mean that is the case on all R2 actually, but let's try to look at this compact set. And again, we will prove some inequality on this compact set, and by using, again, I'm like foreshadowing the things that we are going to derive, and by using the homogeneity properties, and wait a sec, we will derive that, and we will take advantage of that, and we will say, okay, that inequality actually holds on the whole R2. Okay, we will do that. Okay, I'm continuing. There was some problem with my pencil. Okay, and yeah, and v dot satisfies this inequality, all right? And we can write that basically. Okay, so far we haven't written anything new, and all right, here's the thing again, and here's the thing. All right, like it might take time for you to see that, and that's totally fine. Also recall that that is the expression, all right? And we basically use the homogeneity property of v, all right? And on the compact set, here the compact set definition again, and I will try to show all the expression in one page. I will not be able to show that in a moment, but okay, let's see what happens. And this is the case. Okay, this is the case. Why? Because this is 1, right, on that compact set. So that's why we did it. Okay, and let's try to solve for k. Here is the expression that we have, and let's find a square. Okay, this is the expression. This is straightforward, I think. Okay, so using that in the inequality, which inequality? This inequality. Okay, yeah, here is the inequality, and yeah, first inequality, and then we will use this expression. And basically we will try to, yeah, substitute k. Okay, this expression, and here is the expression, all right? And then we can write this, and then we can write this. I'm hoping that it is kind of like step by step, derivation of that, the final thing that we were trying to show that. And since you can see that v dot is, c times alpha, where c is positive and alpha is like that, right? C is positive, and this is the FTS inequality. Or if you can show that on top of like v being positive and v dot being negative, you can show, like, you can immediately say that FTS is the closed-loop system traits. Okay, and that's it. Let me wait a second. Let me show. Is there anything else? No, everything's fine. Okay, wait a second. Okay, that was the final expression. So that's it, and thanks for watching. Don't forget to subscribe.